There we go. Does anybody have any questions yet on the homework? Nothing? Solved them all? Okay.
So that's how's it over
Tricky, like it took time and you were able to figure it out, or you want to look at something on it?
We just go over it, how you would do it? Yeah,
sure. Yep. The other thing that I noticed, I'm able to watch the thing on my computer, so I know that there's hope for the video from Tuesday, but over here, it's pretty dark and it's tough to see stuff. So I'll try and just put, terminology, things that come directly out of the book over here, and then we're working on problems, I'll put them up over here, okay? So that it'll be easier for you to look at them when you're looking at it online. Okay, so what problem are we looking at? Why don't you give me what the setup is for it? Move us along a little bit faster.
Scaling triangle, 6.3, 4.2, and then 6.
Okay.
6.8. And we have one angle.
Looks about like that, right?
Yeah.
And is it pinned here and here?
We want, so that we have that angle, that's 40.
Yep.
And then we want to find these two, but then we're given all three side lengths.
We have all three sides.
6.3, 4.2, and 6.
So 6.3 here,
No, 6.3 at the top left.
6.3 here,
Yep, and then
6.0 here,
Yep, and 4.2.
4.2 here.
Yeah.
Okay.
And the angle for 4.2 is 40.
So do that a little bit, right? And this is 40?
Yeah.
Okay. And so what are you asked to determine?
Both the other two angles, so B and then I think it's like an infinity symbol. I'm not really sure.
You want this,
Yeah.
and you want this,
Yeah.
right? Alpha and beta? Okay. So, what are some things that you could think about that you could do? What would be a real easy way to do it?
You get one angle and then subtract from 180.
Yes.
You like last.
Yeah. I see what you're saying. Yeah, as soon as you find one, you know what the other one is, right? Yeah. Do you remember law of signs? Did you learn law of signs at any time? So law of signs tells us that the ratio of the sine of some angle, here we'll call it alpha, to some triangle length, we'll call it A, is the same as the ratio of sine of beta to B. And I don't know, I'm not up on my Greek alphabet terms, I don't remember. Okay? So this is one way that you could solve it. Right, where this is what we don't know, this is what we don't know, and we can use this knowledge to solve them individually. Okay? Alternatively, you could also use what's known as the force polygon. Okay, and that was one of the things that I wanted to talk about today. But, so maybe we'll just use law of signs to solve this. Then I'll show you with an example how to do the force polygon, which would be an alternative way to solve this. Then we can talk a little bit about coplanar and parallel, and then we'll talk about the lab. So, how are you going to set this up? Which one do you want to find first? Doesn't really matter.
Yeah, let's go for beta.
Find beta? Okay, so sine of beta over B has to equal sine of, I think that's gamma. I don't remember.
B, so you put 6.1.
So you got 4.2, right? What do we say B is? B is 6.3. And sine of gamma is sine of 40 degrees. Okay? So you just have to do a little bit of algebraic manipulation. So beta will be inverse sine of 6.3 times sine of 40 degrees divided by 4.2. Okay? Check and see if I need to write this bigger. Yeah, okay, a little bit bigger in the future. It's passable, but. So what do you get when you crank on that?
We get about 74.
74 degrees, which looks,
I think, yeah.
I mean, for some poorly drawn freehand, right? Looks reasonable.
Yeah, 60.
Yeah, what? 64?
When I did it before, yeah.
Okay.
Could be wrong.
What else are we getting? Anybody getting anything else? Split the difference? What did you get, Zach?
I had 74.58.
74? Okay. Anyone else calculate it?
I got 74 too.
Yeah, 74 also. Okay. So, Matt, you may want to just check your math there. 74 sounds like what we're coming to. I don't have the key right in front of me. You got 74 now? Okay. Okay, so then from there, you could set it up again, solving for sine of alpha, right? Or you could do as Matt said, now that we know two of our angles, we also know that all three of our angles have to sum to 180 degrees, right? Okay? So that is one way that you can solve them. I'll give you a minute to write down any of that information. I'll set up another way that we can do it with another problem that's going to come out of the book, where we use what's known as a force polygon. $60, $30, 100 pounds.
Is that because we minus the sine one?
It's 270.
I think I just.
Okay, so the example that we'll look at comes from page 16 of the textbook. And so what we've got is, I don't know, maybe this thing's attached to a crane, maybe it's attached to a ceiling. We don't know everything about it. But we've got a 100-pound mass, well, a weight of something, attached, and we're distributing the forces, okay? And what we're interested in knowing is what kind of cables would we need to be able to suspend this weight, okay? And we'll look at some of this stuff in lab next week. This is really going to tie it into everything. And the idea behind the force polygon is that if you have a system of forces that are all in static equilibrium, it doesn't matter how many forces there are, 3, 5, 7, 1,019, if they're in equilibrium, you will be able to draw a polygon with that many sides that will close. Okay, so in this instance, we have 3 components carrying force. Okay, so if this thing is in static equilibrium, we should be able to draw it in such a way that we have a closed polygon. If instead we draw it and it looks like that, this thing is going to be moving on us. Okay? That's what it tells us. And so that's another of the ways you can solve these problems. And so you have to use the information provided in the problem to determine what we have going on. So let's look at how we can construct this thing. So how do we take each one of these force components and arrange a polygon with them? What would you like to do first? What do you think would be the easiest component to draw first? Maybe this will help too. We're assuming that this is suspending perpendicularly to the floor below us. Okay? So it's hanging completely vertically. Which one do you want to draw first?
Right triangle.
Well, do we know that we have a right triangle yet? But what do we know about this? If we know that it's perpendicular to the floor beneath us. I guess also we have a perfectly level floor. Okay? We hired an incredible contractor. Made us a perfectly level floor. This is perpendicular to it. What do we know about this? It's going to be perfectly vertical then, right? Okay, so if you find any components that are either perfectly vertical or perfectly horizontal, that's what you would like to draw first. Okay? So we'll draw our 100-pound perfectly vertical component. And this force is acting down. Okay? Now, what about these two? What do we know about them? Do we know the magnitude of the forces acting on them currently? You do? What are the forces acting on them?
50 pounds on each side.
Ugh. Might not be a safe assumption,
Oh, yeah, right.
right?
Yeah.
Because they have different angles.
Right.
If they had the same angle, I think that's a safe assumption to make. Because they have different angles, we should assume that they're going to have different forces on them. Okay? And that's fine. I'm glad that you took a shot at it. So, if we don't know anything about the magnitude, what do we know about them? We know how they're oriented, right? With respect to what? The horizontal or the vertical? With respect to the horizontal, right? We know that the force acting here is going to act 30 degrees from the horizontal. Okay? So let's start right here. And we'll put our force in. And we'll say that I can do a really good job of representing 30 degrees. And let's call that, actually I should check and see. Does they give them identifiers in the book? Let's see. It looks like they're saying that this is A, this is B, and this is C. Okay? So here we have A, here we have AC. Okay? What do we know about this one, AB? How is it behaving? We don't know its magnitude, but what do we know about it? that?
It's angle.
We know it's angle, right? This one is 60 degrees from the horizontal. So now if you come through and poorly join those up, with that angle being 60 degrees, now we've got a closed force polygon. Okay, so we've set up the condition where this thing will be at static equilibrium, which is what we want. We want to make sure that when we hang this 100-pound force, we don't tear that pin out of the ceiling, we don't tear that pin out of the ceiling, or worse, tear both pins out of the ceiling. Okay, crushing whatever equipment or people we've got below. So now we have to figure out what's going on, how can we solve this thing? Okay, so using properties of triangles, what can you tell me about this triangle? Maybe this thing needs to be bigger too. Gavin, would you take a peek? Can you tell anything that I wrote up there? I have a feeling it's got to be bigger. Can you see that pretty clearly? Not at all.
Barely.
Okay. So think about it. I'm just going to redraw it real quick so that when you're playing the home version. It's not good at 30 degrees. Better. Let's see. So AB. AC. Okay. So what do we know? What do we know about this angle? We'll call this alpha. Why is it going to be 60 degrees? Yeah, we said this thing is perfectly vertical, despite my poor freehand drawing, right? And we also knew, Matt told us, that this force is applied 30 degrees from the horizontal. So if this thing is perfectly vertical, and this angle is 30 degrees, alpha has to be 60 degrees. Okay?
What does that mean?
What's that? What does it mean? Right,
No.
right now it just means that it's 60 degrees, but that's going to help us, right? So, come on. What do you know about this? What's that angle?
90.
That's got to be 90, right? Because this is perfectly horizontal, this is perfectly vertical. So, what's this angle? 30 degrees, right? Because now we've made a little triangle. So if this is 30, and if this is 60, what's this angle? Now we've got a right angle, despite my poor drawing skills, right? Freehand drawing of triangles is not a prereq for teaching this course, okay? So, 60, 90, 30 degrees. What do we call that? We call that beta. Okay, now how are we going to solve this? Say it louder.
Law of cosines.
You could do law of cosines.
Wait, is 100 pounds length?
100 pounds that's the magnitude, that's the length of it, yep.
Clarify
Wow,
what
so
We want to know how much of the 100 pounds is being picked up by both of these cables. Okay? And because at Zach's question, he said, what is this? This is 100 pounds. So if we solve this triangle, it's going to tell us the force carried by AB and the force carried by AC. Okay? How do you want to do it? You could do law of cosines. I think law of cosines, you have to do too many steps.
See, I didn't know we had a side. I didn't know that the 100 pounds was.
Gotcha. Yeah, so let's apply law of sines again. Where did I pick up red from? So, AB has to relate to sine of alpha, right? Just as AC has to relate to sine of 30 degrees, right? Just as, yeah, let's get rid of that thing. Just as 100 pounds has to relate to sine of 90 degrees. What's sine of 90 degrees? It's 1, right? When you think of the unit circle. Okay, so these ratios all have to equal 100. And what's sine of alpha? Or sine of alpha. What's sine of 60 degrees?
Sine of 60, 0.8660.
Okay, so AB point, so it's 87?
Essentially.
It's in 0.125 for sine of 60 degrees?
Sine of 30. For AC, it'd be sine of 30.
Oh yeah, so, sorry, sine of 30 degrees? 0.5.
think I typed that.
Oh, yeah, I'm sorry. I'm thinking of doing moments where we have to sum them, right? So 87 pounds being picked up by AB, 50 pounds being picked up by AC. Okay? So, and that could help you if you need to know, hey, how are we sizing this cable? If we've got a bunch of 3/8 inch diameter cable laying around the warehouse and a bunch of 3/4 inch cable laying around the warehouse, and the 3/8 inch cable has a limit of 75 pounds, we're good to go using that on AC, not good to go on AB, okay? But really, we're probably using the 3/4 inch just to make sure that it doesn't get installed incorrectly, okay? But that's the application of what we do with these. Now, the other thing I want to make sure that you understand is when we're solving our force polygons, this does not tell us anything about what the actual length of any of these items are, okay? It's telling us the force that's being exerted on them. What that means is we're using that to not determine what these two-dimensional items are going to be, but what a three-dimensional thickness of that cable needs to be. Okay, does that make sense? The length of these are simply going to be defined by the physical space everything is taking up. Okay, I think that's an important distinction to understand, that the force doesn't necessarily directly correlate to the length of something. Okay? Questions? Okay, so I think that'll help you with those two force polygon questions in the homework set. Okay, so those are the three types of problems that you have for the homework, right? So we did the force polygon today. On Tuesday we did the force resolution. We also did the simple beams where we're doing the moment calculations, okay? So that's due, what did I make it due? I think it's next Tuesday? What's that? Is it until Thursday? Okay. Okay. So crank on those. If you got questions, let me know. Those of you who are traveling, if you got questions on them before you leave, throw me an email, and then we can meet up when you get back on them, okay? All right. Let's see. Couple force terminology items. So looking over the terminology quizzes yesterday, a couple people, no one really got tripped up on much, which was good to see, but coplanar and parallel tripped us up a little bit. So I just wanted to talk about those concepts a little bit before we go forward. So if we're dealing with a parallel force system, remember that when we're talking about our force, we've got some magnitude, we've got a sense, and we've got a line of action, right? So the magnitude is how much? 100 pounds, 87 pounds, 50 pounds, okay? Sense is which way is it going, right? And then the line of action. Now, a thing to remember about a force is we can move it as long as we don't change its sense, and as long as we don't change its magnitude, we can move it anywhere along its line of action, okay? Think about if we were to throw a baseball with a force of 50 pounds at this wall. Does the wall care if we throw it from here with 50 pounds, or if we throw it from here with 50 pounds, or if we throw it from here with 50 pounds? Now with respect to the 50 pounds, now that increase in distance may translate to the amount of damage we do to this thing, right? Okay, but that's a different concept. Okay, so 50 pounds of force, we can move it along this thing anywhere we want as long as we aren't changing its sense. Okay, as long as we don't try and rotate it anyway. So where people got tripped up was confusing coplanar with parallel. And I think the easiest way to think of it is a force would truly only be coplanar if we think about this wall, if it's only acting in the plane of this wall. Okay, and another easy way to think about it is think about the roof load on top of us. Okay, I know that there's another level of flooring up above us, but as that roof load is transmitting down, there are forces getting pushed down through this section of the block, through this section of the block, through this section of the block, and through this section of the block. Okay? If we go to the back of the room and look at the brick wall back there, and we'll ignore the fact that there's a door cut out and the effects of the forces moving around the door. Let's just focus on the section of block where there isn't a door. Are those forces going to be relatively the same to the forces up here? They're going to travel in the same direction, right? With about the same magnitude. They're trying to get down into the earth. Those would be parallel, okay? Because they aren't operating in the same plane. Yes, they're moving down like this, right? But they have a different line of action than the forces in this wall, okay? Also, if we think about this wall, as it's coming down to the floor, what is happening from the weight of yourselves and the desks? What is the floor trying to do? Does the floor want to hang on to your weight, or does it want to push it down into the ground? Wants to push it down into the ground, right? So the force of our weight and the weight of the desk is coming into the wall, okay? Some of those are getting picked up by the wall, but some of them are transmitting through to the other side. Okay, so those also would not fit into coplanar, okay, because they're traveling through that plane. Does that help understand that distinction? Does that help understand that distinction? Does that help you understand that distinction?
Yes.
Okay.
So it would be coplanar. What's an example of coplanar?
What's that?
What's an example of coplanar?
Coplanar would be the forces coming down. Yep. Yep, it'd have to be all acting within the plane of that wall. Once it starts acting in a different plane, if we started trying to overturn the wall, no longer coplanar. If we're going through the wall, not coplanar. Okay? Everything's got to operate through that same plane. Good question. Okay. Let's see. So the last little bit, we'll maybe get done a little early then today. Turn this on. Next week, we'll do a lab that will help you kind of visualize the concept of forces. Oops. So as this thing finishes warming back up, so you see we've got a submission point for lab 1. Just like in the materials classes, you only need one submission per group. You get to work in groups. You don't have to work on your own. That's how you're going to work in the real world. Just make sure that everybody that's in your group, you put a name on it, okay? So that everybody gets credit for it. So that's where that's located in the week 3 module. What we're going to look at doing, I should have taken a picture of the thing. Or maybe if we, I don't know. It's up to you, I guess. If you're interested, we can go down to the lab and take a look at it afterwards. But let's zoom in on this thing a little bit. I'm going to zoom 200%. There it is. Okay, so when I first taught this class, here, I'll turn off the light so we can see a little bit better. Oh, not those ones either. Get it on the last one, I guess. To kind of help the students understand this force resolution, because it can be it's a pretty tricky concept. We made these plywood boxes. So what we do is it's a 5-sided box, so you've got an open face as you're looking into it. And we pounded in a bunch of fencing nails, 4 inches on center, on the back wall, the top wall, and the 2 side walls. Okay, so you can tie into the sides, the top, and the back. I forget, maybe there's some on the bottom, I don't know. But we've got some weight systems, we've got some cheap little fishing scales, we've got various ropes and cords, and then you'll need a calculator. Okay, so you can try a bunch of different setups to see, as you change around the orientation of cords and ropes, what happens to your force system. And the idea behind it is, I give you some coordinates to work on, so you can look at what's going to happen if you can model essentially what it would be like if we're picking with a crane. Right, okay, what's going to happen to the forces in there? We can use ropes to set up horizontal and vertical to model beams and columns in a structure. Okay, so it's a way to help you visualize what's going on with a loading system. Okay, yeah, and so that's what we say here. So we look at supporting a weight by 2 supports that are anchored and supporting a weight through 2 horizontal supports. And so what you're going to do first is you'll just take the weight set and determine what's the mass of the thing. Okay, so you know what it is that you're suspending. After that, then I just give you a bunch of directions. Okay, and so I talk about the X, the Y, and the Z coordinates. So we'll have to draw 3-dimensionally on a 2-dimensional board. And we're probably all familiar This is X, this is Y, this is Z, right? But if you think about the board, where in actuality the dashed line is going into the interior design studio behind us, and this axis is coming out at John. Okay, so we're talking about our Z-axis. So that's when you're working with, if this is your box, your Z-axis is coming into and out of the box, okay? The Y-axis is up and down, is vertical, your X-axis is still gonna be horizontal. But that's what I mean when I'm talking about X, Y, and Z coordinates, okay? So, telling you to, you can move them around on that roof. You can move them around as much as you want in the X direction. I just want to make sure that you keep them static in the Z direction as you're changing them around, okay? And then you're just going to support between two bungee cords, record the amount of mass suspended from both of those supports, okay, to see. And then you can use that, you can figure out the distance between, you can use it to figure out angles, okay? Yeah, recording accurate distance, that will help you. So, we didn't go through and, I mean, the precision on the 4 inches between the fencing nails is probably not real great, okay? But you can assume, for the purposes of the lab, that all the nails are exactly 4 inches apart. We don't have to determine whether it's 3.92 on the one and 4.14, okay? Just assume you've got 4 inches between all the nail supports, okay? And then after you do the first case that is described to you, you'll consider 2 other cases, okay? And all that you're gonna do is moving your supports along the X direction. So you're just gonna move your supports farther apart or closer together to see what that does to your loading conditions, okay? And think about it conceptually, okay? When we talked about that force polygon,